Good day, everybody, and welcome to today's webinar on Discrete Event Simulation. My name is Pranav Vishwanathan, and I am Business Manager at NetSim. And along with me is Sonia, who is an Application Engineer. The agenda for today's webinar would cover an introduction to simulation, understanding the difference between discrete and continuous systems, event generation and event handling, study of queuing models. After this, random number generator and events involved in NetSim simulation, understanding the virtual network stack of NetSim and the supported protocols in different layers. And finally, understanding how to implement your own protocol in NetSim. This webinar is not a webinar that is focused on NetSim, but rather a webinar that focuses on the fundamentals of simulation and discrete event simulation, and hence it would be fairly theoretical in nature. So let us start with an introduction to simulation. What is simulation? A simulation is the imitation of the operation of a real-world process or system over time. And some of the steps involved in a simulation is to generate the artificial history of a system, observing the behavior of that artificial history, and drawing inferences concerning the operating characteristics of the system. The behavior of a system as it evolves over time is studied by developing a simulation model. This model usually takes a set of assumptions concerning the operation of the system. Once developed and validated, a model can be used to investigate a wide variety of what-if questions about the real-world system. Let us now see how to create a small network model in NetSim. So this is the GUI of NetSim, and we'll go into one of the technologies called internetworks. Here you can see the different network devices that are available, and this GUI can be used by our users to model a network. So in this case, we will click and drop a few devices. This is a router, and then a switch. Then we are adding some wired nodes, and on the other side we are adding an access point and a wireless node. We are connecting the devices using wired links, the wired devices, and the wireless interface is connected using a wireless link. So as you can see, with a few quick steps, we have been able to create a small network model. The next step would be to add some traffic flow in the network, and that is done by clicking and dropping the application icon. And here we set two applications. One is known as a CBR, which is a constant bitrate application, and the other we will choose a voice application. So as you can now see, we have set two applications. One is traffic going from 3 to 6, and the other is a voice application going from 4 to 6. We will now simulate this. And at the end of simulation, we get a series of network metrics that are useful. I'll not go into the details of the metrics. The entire simulation can be visualized using our network animator. And as you can see over here, you can see different kinds of packets flowing between the various devices. And we have information related to what is the kind of packet, whether it was successful or errored, simulation timestamp, and so on. So this is to give you an idea about how you can create a small model of a network and simulate the same. This slide talks about the difference between discrete and continuous systems. This is important because NetSim is a discrete event simulator, and if you see the first figure, one of the taps is having drops of water, which is discrete, whereas the other tap is continuous water, which is a kind of a continuous system. So discrete system is one in which the state variables change only at discrete points in time, whereas a continuous system is one in which the state variables change continuously over time. And the bottom half talks about how is NetSim's discrete event simulation. So on the x-axis is time, which is increasing, so time is increasing like this. And here you can see a number of events, E1, E2, E3 and so on. E1 and then E2, E3, E4, E5 are closely placed in time, and then you have E6, then E7, E8 and far away E9 and E10. So in NetSim you must understand that time jumps from event to event. So whatever is T1, the time that is appropriate for, that is set for E1, and then time will jump to T2 and then to T3, T4 and so on. There is no question of anything happening in the time between the events. So between E8 and E9, there is no concept of time. Whatever is the time at E8, the next time would be E9, which is the next event. This is the essence of a discrete event simulator, which is what NetSim is, whereas a continuous time simulator would have time continuously increasing. In NetSim, time jumps based on the events. Now some quick terminology about simulation systems. The first is a model. A model is an abstract representation of a real system for the purpose of studying the system. For example, in NetSim, it could be a particular network of interest and its parameters. The result of a simulation, the result of any simulation is based on the model that is input, and hence creating the right model is of vital importance. And as you saw in NetSim, the graphical user interface helps users to quickly model the network. Then another term that is used commonly in simulation is known as simulation clock or simulation time. This simulation time is a user input in NetSim. Simulation time is a variable that represents the simulated time, and we'll just show you this in the GUI. So this is where the simulation time can be set, and please note that this is different from wall clock. Wall clock is the time that is the real time that is taken by the server or the PC to complete the simulation. Then going back, so you have events. We've already spoken about events. Entity is nothing but some part of the model. This could be an access point or a router, or in another context a customer or a machine. The state of an entity is defined as the collection of variables that contain all the information necessary to describe the entity. For example, this could be a node in backoff, could be a state, and finally an attribute. So if you see a node has a set of attributes. You right click on the device, you have a set of attributes. So these are, for example, all the wireless attributes of the device. Now we will talk about queuing. Queuing is fundamental to any network simulation because packets arrive and get served in all devices. In general, the term arrival can refer to people, machines, packets, and so on. Anything that arrives at a facility and requires service. The term server refers to any resource, person, machine, etc., which provides the requested service. A queuing system is described by its calling population, the nature of arrivals, the service mechanism, the system capacity, and the queuing discipline. A single queue system is characterized by having a single waiting line organized according to some queuing discipline. Some of the queuing disciplines in NetSim which we will be showing you are FIFO, priority, round robin, and weighted fair queuing. So these queuing disciplines are available in NetSim. So you can see that these are some of the queuing disciplines that can be set. Just a second, we got a few questions in the middle that they were not audible, and I hope things are clear now. In case of any doubts, you can please write to us in the chat box. Another question was whether this can be used for modeling 5G networks and so on. I'll answer all the questions at the end of the webinar about what technologies are supported and so on. In the meanwhile, in case you have any difficulties with regards to hearing or viewing the webinar, please let us know. Questions I will be answering at the end of the session. The next thing we will talk about in NetSim is event generation and handling of events over time. So this is a typical example so that you can understand about discrete event simulation. The figure depicts the number of customers in the system at various points in time. Customer 1 is in the system from the 0th second to the 2nd second. Customer 2 arrives at the 2nd second and departs at the 3rd second. No customers are in the system from the 3rd to the 6th second. During some periods, 2 customers are in the system, such as the 8th second, when both customer 3 and 4 are there. Also, there are times when events occur simultaneously. So this is important. In NetSim, you can have multiple events occurring at the same time. In this case, in the 9th second, if you see, you have a customer who arrives, customer 5 that arrives, and customer 3 that departs. So earlier you had customers 3 and 4, and now you have customers 4 and 5. So this is a very simple example about how a discrete event simulator would be working. NetSim, of course, is a much more complex process than this. And this is to give you an idea about how fundamentally discrete event simulation is run. Next, we'll talk about queuing theory. And in this, we will be talking about, to start off with, the most simple queuing system, which is an MD1 queuing system. This notation, where you see M/D/1, is called the Kendall notation. The first variable stands for the arrival process. The second variable stands for the service time distribution. And the third variable stands for the number of servers. As arrivals are Poisson in nature, they are notated as M. Since service time is deterministic or constant, it is notated as D. And we have one server. So how do you model an MD1 queuing system in NetSim? The first thing that we do is we set up a small network like what is shown with 2 wired nodes connected to a router, and then we generate traffic going from wired node 1 to wired node 2. And again, I just like to reiterate that NetSim can be used for simulating a variety of complex wired, wireless, sensor, mobile networks, etc. And here is just a small example to show how simple MD1 queuing system can be set up. Once we set this network up, we change all the parameters, or rather we disable all the parameters of the protocols, links, devices, etc. so that we focus only on the queuing aspects and we eliminate everything related to the network protocols. We'll be showing you the network in NetSim. So we've already saved this, and then we'll be opening a saved experiment. So here is the network. In this, what we do is, in the application, we set the inter-arrival time as 2000 microseconds, and set the distribution as exponential, whereas we set the packet size as 1250 and set the distribution as constant. So when you set the distribution as exponential, this is the method of generating Poisson arrivals in NetSim. That is, you want to get, I'll be explaining about Poisson arrivals later on in the simulation. The idea is that you want to get a randomized, you want to get random arrival times, but with a mean of 2000 microseconds. That is done using the exponential distribution. And to get constant service rate, you set the packet size as 1250. So one of the questions here is, can you set an MMN simulation in NetSim? Yes, definitely you can. You just need to set multiple devices and you get MM. If you change the packet size to also exponential, you will get MM. So using that, you can get an system, MMN system. Then there's a question, can NetSim be used to check the processing time of a firewall? We have firewalls available in NetSim, and for processing time you can you'll have to go in and possibly make some changes in the code. There's another question regarding the distributions. I am just coming to that in the next slide, and I'll show you the distributions that we have available. So now, having done this, let us just look at the parameters that we have set is packet size 1250 and inter-arrival time 2000 microseconds. Now note that this is what is happening in node 1. So in node 1 you are having packets being generated and then they are being served by that link. So queuing occurs in the node, in one of the buffers in the node. That is due to random arrivals at some points in time. The arrival rate is greater than the service rate. Hence queuing occurs. And the theoretical formula for calculating queuing time is given as 1 by 2 mu into rho by rho minus 1, where mu is the service rate and rho is the utilization. Utilization is defined as arrival rate by service rate. And if you were to apply this formula, you would note that the theoretical queuing time got for our model should be 569 microseconds. And we now run the same, we have run the same simulations in NetSim, and there's a formula to calculate the queuing delay. And here you can see that when we set 2000 microseconds, the theoretical value is 569. And in NetSim you get again something very close, and similar for 1500 microseconds. These are results of 100 seconds of simulation, and generally the longer the simulation is run, the more accurate is the simulation results.